Walter Shawley was one of the most knowledgeable individuals in the vintage tech space, and an excellent supplier of a wide variety of tubes and slide rules. Lachlan Van Egmond interviewed him as part of a project outlining the history and technical function of Soviet gas-filled and vacuum tubes. The following is that interview. Interviewer, Lachlan Van Egmond. Interviewee, Walter Shawley. Date, July 2022. Could you tell us a bit about who you are, what you do, and primarily how you got into the vintage vacuum tube and parts business?
My name is Walter Shawley. I run Sphere Research. Before that, I spent 25 odd years in the avionics industry, designing, developing, and looking after avionics systems, which is basically anything electronic that goes in an aircraft. As a hobby, I've always liked test equipment, basically anything interesting, well-built, that does something useful. So now that I'm retired, I still look after and offer test equipment and things like slide rules to people who have similar interests. I've worked with lots of equipment that has Nixie tubes, basically every kind of display from light bulbs in a row, pneumatrons, CRTs, LEDs, what have you.
Was working with Nixie tubes and other displays common in avionics? I know their use was common in general, but specifically in avionics, would you see Nixie tubes and such in the cockpit?
Nixies are not that common in the avionics world, but they are quite common in test equipment. Consider what a Nixie tube really does. It's a true form numeric indicator, so when you look at the number 2, it looks like the number 2. For a long time, people only had analog instruments, something with a meter on it, or a magic eye tube, or something useless like that.
Like a D'Arsonval-type galvanometer?
Yes, because it just wasn't possible to generate the data in that digital way. So, in the late 50s, early 60s, there was a big push for digital circuitry. It really started making big inroads, and people were able to design and build equipment that could make use of that. So, you could have a voltmeter, for example, that could display 3 significant figures. Well, that might not sound like much, but believe me, before that, it was very, very difficult to do that. With a meter, the best accuracy you can hope for is around 1%. Probably not that accurate over the full span of the meter. So what you're really saying is 2 significant figures. So it's not a very accurate measurement. If you're trying to do more precise stuff, like go to the moon or build a big power station, there's that need for a higher degree of resolution. Right. I want to be able to show something with multiple figures. If I want to measure frequency, I want to measure down to the last hertz. Let's say I have a TV station and it's operating at 56 megahertz. I want to know that exact frequency because that's an FCC requirement. As a transmitter, I have to be on the right frequency. Doing surface on that or doing anything related to that, I have to be able to measure that. So how do you do it? What was the technology before this kind of stuff came along? Well, it was not very good. It was things that had meters on them, like trying desperately to give you high accuracy with a low resolution instrument. But once you get to the point where you now have the ability, let's say I'm measuring frequency because that's one of the easiest. Pulses come in, and you count the pulses and use that to drive some type of display. In early technology, that was done with everything from electromechanical counters to rows of light bulbs, like 10 light bulbs in a row. I actually have a counter that is built that way.
Ah, like the strongman game at the fair where you hit the plate with the hammer and it goes up however far and rings the bell based on the strength of the hit.
Yes, but in this case, let's say you have 5 digits of resolution. Each digit is a row of 10 lamps. The idea is the first counter has to be able to count quite quickly because it's being cycled the most. It counts up to whatever, and when it toggles over, it triggers the next row, and so on and so forth. And each row represents something higher in frequency. That was essentially the first concept for making a digital counter. HP had 4 or 5 different models that were like that. This is back in post-World War II, where people basically were trying very hard to make use of all of this technology that they were forced to create during the war. But trying to make measurements with high accuracy requires a system that can display that accuracy. They just didn't have it. With the advent of digital technology, you could do this stuff even if it was with vacuum tubes. Some of these early ones, these rows of light bulbs, were made with vacuum tubes. You can imagine how big and ugly it would have been. Anyway, the thinking was that as digital technology was slowly settling into laboratories all over the world, people were thinking, wouldn't it be great if I could just turn on a digit that looked like the right thing? And that really was the motivation behind the guys at Haidu Brothers, who created that first conceptual Nixie tube. People were using a lot of neon lamps, and in fact, the row of lamps in these counters were in fact neon lamps, because they were very easy to interface to a vacuum tube. They just stretched that a little further and said, well, what if we shaped the electrode so it looks like a number, and we put a grid over the front, and now, when we turn that on, we'll get a number that turns on, and it'll say 1 or 2 or whatever. It was actually life-changing for a lot of technology because it meant you could go from crappy, inaccurate, meter-based, low-resolution systems to things that could actually show you the true value. The impact of that is enormous in terms of precision. You can make way more accurate stuff than that. Burroughs pushed that technology. They bought the rights to the Haidu Brothers design. Their first efforts looked much like the final ones. They just got bigger and smaller. But the idea behind it is really simple. You put neon gas in the tube and have a cathode that you ground. You tie the anode to plus 170 volts through a limiting resistor, and when you ground that cathode, it lights up, and you see the number 2 or 6 or whatever. There's an enormous amount of clever technology behind it that makes it work. The right gas pressure, some additional mercury diffused within, the right stacking distance, the right insulation. But the beauty of it was I could show you the frequency and you would unambiguously know what it was. That was probably the biggest leap in technology, the ability to go from low resolution stuff to high resolution stuff, and Nixie tubes were right at the beginning of that. They were the first way of doing it. One of the interesting things about Nixie tubes is that the physics behind ionized gas is not very intuitive for most people. The whole idea of ionized gas seems like it should be simple. Neon lighting has been around for a long time with very high voltage outside of theaters and open signs in restaurants. This is just another aspect of that, except this does not depend on secondary emission. Neon tubes have ultraviolet radiation being generated internally, which lights up the phosphor. The phosphor is what makes the red, blue, green, yellow color. In the case of Nixie tubes, it's the actual glow of the neon gas itself. The ionized gas that makes the digits, so it's much simpler. But like everything else that's simple, it's always deceptively simple. Getting it to work properly is tricky, and Russians cloned a lot of these devices, and you can buy lots of them off eBay. But a lot of them don't work properly because among the things they weren't able to get correct were gas pressures and insulation. So you get these and they will flash over or arc over, and they just don't run right.
Legend has it that the 2 became used as the 5 because there was something in the Politburo or whomever decided to flip the 2 and make the 5-digit.
Yes. Well, whoever made that decision was clearly not somebody who appreciated the art of what they were doing. So some guy who said, look, I can save 4 kopecks by flipping this over. When you see them today, like in the IN-14, which has that flipped 2 and 5, it looks like crap. There's just no way to dress it up, you know? You can put lipstick on it and it still looks like a pig. Strangely, they made a smaller version of the tube, the IN-16, which has true form characters, so the 2 and the 5 look correct, and that looks 1,000 times better, but there's no accounting for taste. People do what they do, and you just have to grin and go, oh yes, that's really ingenious the way you did that. But the whole point behind Nixie technology was to give you true form characters so that anybody looking at it knew what the hell they were looking at. That was really the whole point of it. Then as you kind of drift into the 70s, the big shift was to things that could be read in sunlight, which a Nixie tube is not good for, along with things that could be powered by a different kind of technology like LEDs or LCDs or pneumatrons.
Because Nixie tubes are very high voltage relative to LEDs and pneumatrons?
It is not that easy. You need at least 150, usually 170 volts to light one. So not everybody who has a battery-operated instrument has conveniently located 170 volts to run it.
Then you have to spark the tube at an ignition voltage, and then you have to sustain a certain voltage, correct?
Yes. And the thing that's interesting here is that if you take that Nixie tube down into a coal mine, it may not fire because there isn't enough stray radiation or photons to trigger the initial strike to make the gas glow. And they discovered this when they were trying to put some of this instrumentation on things like submarines and put them down into coal mines. So they had to put some radioactive krypton gas in the tube. This was so that it always provided a very tiny amount of background radiation that helped start this ionizing cascade, which made the gas appear lit. So that's a strange byproduct of all this. It's interesting technology, and as I said, it's deceptively simple, but there is actually a lot going on behind there to make it work properly. Anyways, the shift was eventually to what we call 7-segment displays, really ugly, blocky characters.
Wasn't the intermediate between Nixies and LEDs pneumatron tubes like the Apollo IEEE pneumatron?
Well, pneumatrons were an attempt to make something that was sunlight readable, because you can't just see a Nixie tube in sunlight. It is just not bright enough. So things like when you were trying to put a digital display in gas pumps, a pneumatron is sunlight viewable, and that was also the technology that made its way into the cockpits of airplanes. Believe it or not, it was also very popular in nuclear reactors. Pneumatrons were a big favorite, and that was the worst possible choice because, of course, the thing with a pneumatron is you can burn out a filament, and now an 8 looks like a 0. It was one of the few displays that had a fatal built-in flaw, so I would not have personally put it into a nuclear power plant, but we still sell them today to guys who are operating nuclear power stations because that's the instrumentation that's in there. But cockpits, we're very happy to see that technology because it did allow them to have sunlight viewable displays, which which was a big deal. So a lot of communication, navigation radios, and other displays were built using that type of technology. And they used some special techniques to lengthen the life of the filaments so they could get very, very long service life out of it. And they would also do a power on self test so you could tell that the display was working before you started. Anyways, that technology lent itself to being converted to LEDs, and although it took a lot of special optical screwing around like light pipes, we happen to make LED 7-segment displays. That came with the market, and that was the way everyone built 7-segment displays, whether it was an LED or LCD or vacuum fluorescent tube. That eventually became the magic way.
In the technology timeline, do we go Nixie and then VFD or Pneumatron?
Well, VFDs and Pneumatrons kind of coexisted at the same time. Pneumatrons are still very much alive today as are VFDs. They see use in a lot of consumer equipment from microwave ovens to CD players. VFD allows a lot of customization. If you're the guy making the VFD, you can add symbols and characters and pictures of CDs and whatever else you want for your microwave oven, little bars and whatnot. That's why they're still popular, but they're slowly fading away as people are going to a more general purpose microprocessor-based display using, say, an LCD display.
Can you explain VFD construction?
They have a filament inside which stretches out, although you can hardly see it. It stretches all across there, and you have a cathode which has got some phosphor coating. The idea is that you make electrons flow there, it makes the phosphor light up, and now you see something. That's exactly the same concept that's used in the Nixie tube with ionized gas, but in this case, it's inside of a vacuum. It's just electron flow. Now, the beauty of that is that it is possible to build very, very sophisticated VFDs as long as they are parallel displays. In other words, I can't stack objects up like I can in a Nixie tube. That's not possible to make that work, but I can put 20 different characters side by side and add a bar graph and a picture of a clock.
Oftentimes, you will see custom VFDs and radios that have the pause button and the play button, among other things. I've seen many more VFDs that have custom small buttons when compared to Nixie tubes.
Yes, you don't see very many symbols in Nixie tubes. They were basically for digits, and they had some that had individual characters like K for kilo, plus or minus, that were for use in things like digital multimeters or what have you, but they would have an ohm sign. They would have the letters AC or a little sine wave that allowed you to display not only value, but what parameter you were measuring. So there was a certain amount of that, but all of them together represent maybe the letters of the alphabet.
And this is a technological limitation of the Nixie tube.
Yes, because I can't stack symbols on top of each other in the VFD, but I can in the Nixie tube. So I can have 7 different characters, and one could say AC, plus, minus, but this could all be in one display. Therefore, I could have one display to the left of my digits that told you what I was measuring, like AC or plus or minus for DC volts or ohm or what have you.
And are VFDs always bluish green?
It's just a commonly picked variant. They can be any color, and you can also filter them to get other colors. Because I can't stack the characters up, I have to put them side by side, so they have to be parallel. While a Nixie tube is a serial display. The point is, all of them lend themselves to displaying 7-segment characters, and there are Nixie tubes that display 7-segment characters like Panoplex displays. There we don't stack up the characters, but we have that same 8-figure, which is actually 7 segments, which display all the numbers from 0 through 9. So they were actually quite widely used, and they were made by Beckman. Boros didn't pursue that. It's a different kind of technology, but they were pretty successful with it, and that stuff is still around today.
So, I have another specific question because I know you have a tube tester. What is cathode poisoning, and how does tube healing and testing work?
Well, cathode poisoning, as I said, it seems like a simple technology because I ionize the gas around this electrode, but when I do that, there is some sputtering that takes place where metal is actually stripped off the electrodes and gets deposited on another electrode. What happens here is that it can create a non-conductive barrier. So the result is you get only partial illumination of the digit. It typically happens with the digits that are not turned on. So let's say I have a clock and the clock displays time in whatever format. If I look at the left-hand most digit, which only can display ever a 0 or a 1, if I tried to display, like I take that Nixie and I put it in the seconds position, I may discover that all the other digits are screwed up because they were sputtered by this metal that was stripped off the electrodes. Now, you can make them work again by basically cycling through what were previously unused elements, and you run them at a higher current than normal. It takes a while, but once you get the digit to finally strike, then you can slowly back off the current, and eventually you let it run for like 6 or 7 hours. It will work normally after that, but it strips off that coating. It's a very tedious process, but you can restore them 90% of the time. What you can't fix is when the glass turns kind of a silvery color. That usually happens because they ran the tube at too much current and they stripped all the metals off and it sputtered into the glass, and it's opaque, meaning you can't see through it. And now the digit is very, very darkened behind there. For that, there's no fix.
And there's also the difference, if I'm correct, between the silver glass sputter coating and the getter flash. Could you tell me a bit about that?
Well, a getter is really a device for stripping water and undesired gases out of the tube. It's more pronounced in the vacuum tube. Nixies are not vacuum tubes. They are technically gas-filled tubes. A properly made Nixie has little or no getter flash in it. When you look at a tube, it should be clear all the way around. It can have some mercury, and some tubes do have a little spiral hidden underneath the tube which contains mercury. And that mercury is used initially to blend with the gas to give you a more desirable looking view. But a getter is not normally part of the tube. It does occur in some tubes, I guess. It depends on how good the manufacturer was as to whether or not they have to use a getter flash to try to trap whatever those impurities are and basically burn them onto the side of the tube. Normally, when you see a Nixie tube and it has that silver coating, that's because it has been run too hard and it's actually stripped the metal off the electrodes and deposited it around the gas.
What is the difference between heated tubes and Nixie tubes?
Right. It has no heater. It isn't a vacuum tube, first of all. It is a gas-filled tube, so the concept of operation is totally different. You're just going to apply enough voltage that we hit the threshold where the gas ionizes. That's what creates the usable effect, which is the visible appearance of the number. There is no other magical electron effect going on in there. There is no heated cathode, etc. Its concept of operation is totally different from vacuum tubes. It is a gas-filled tube. VFDs are in vac vacuum tubes, and you can actually make them work as a triode if you desire for some purpose. Some guy built a stereo headphone driver using VFDs. VFDs do run like vacuum tubes. It has a heater in it, a control grid, and a cathode with phosphor on it that lights up. It's basically like a little CRT almost, except in this case, it is that little electron that lights up.
I know the Soviet tubes are all the rage when it comes to buying them cheap.
It's because they're available. See, there is no big warehouse anywhere sitting there with thousands of Nixies from, let's say, Burroughs or National. Those tubes have been gone for 30 years. If you find some, it's luck. Somebody had them somewhere, or more likely, they were picked out of a machine. But there are thousands of Nixie-like tubes sitting in Ukraine, in Russia, Lithuania, and after there were several articles about building clocks with Nixie tubes, enterprising young Russians decided to sell them mainly on eBay because there was actually a market for them. Up until that point, they were just taking up space in the warehouses and nobody wanted them. Now, one thing that's somewhat intriguing is Russian tubes strike at a lower voltage, typically 150 volts. American, European tubes need about 170 volts. Now, I don't know whether that's gas pressure or mixture of gases, but it's an interesting difference which happens to make it easier to make a clock with 150 volts, being not as much effort as 170 volts or something higher. Also, as the gas tubes get older, you require a little more voltage to make the gas strike because you do get some gas pressure leakage through the pin to glass seal. Individual characters build up a little bit of sputtering on them, and over time, tubes do need a little more energy to strike.
I was wondering, do you find that the issue is often air comes in or gas leaks out?
Well, it's not like they evacuate. Usually what happens is things other than neon get in, and they become very, very weak and eventually won't strike at all. It's actually a more common problem with Panoplex displays because the steel to glass seal is actually quite good on a vacuum tube or a Nixie tube. That technology is very mature, and they were very good at making them work. But a Panoplex display is a sandwich made out of layers of glass that are glued together. The opportunity for the gas to leak is much greater, and we find over time that you're much more likely to find a bad Panoplex display than a bad Nixie tube. I've got Nixie tubes made in 1962 that still work perfectly, but I've got unused Panoplex displays made 20 years later that won't strike at all because the gas has leaked out.
You're talking about the square ones?
Yes, it's basically a 7-segment display made with neon.
Was the Panoplex cheaper than the Nixie tube?
I think it was cheaper. The Nixie tube is a wickedly complex mechanical device. Like, when you look at it, you think, how the hell did they ever put these things together? There's all these tiny little spider electrodes and insulators stacked up in a little sandwich with a grid over the front. That is a complicated piece of engineering. And to make it so that it doesn't arc over and screw itself when you're trying to energize it, because the Russian ones do that all the time.
Ah, is that a manufacturing issue?
Yes, it's strictly a manufacturing issue. There are guys that have gone back into production, like Dalibor over in the Czech Republic. He makes big Nixies for display clocks and such. He makes a wonderful looking tube, really beautiful. He actually has a bunch of stuff on YouTube where you can see the exact process of how they make all these electrodes and stampings. It's a technology that kind of disappeared. Like, if you had to have vacuum tubes today, most guys would be unable to produce them because they have lost the technology to be able to do it. It has many, many steps in it that are quite tricky.
Sometimes you will see mercury globules in the bottom of the tube. Is that the penny mixture?
That's put in when the tube is first manufactured to help combat effects like sputtering. Normally, it should all be vaporized and consumed at the time of manufacturing. There should not be any rolling around because it could act like a short between something. There are funny spirals underneath the tube that are used to hold the mercury inside when the tube is first made.
Do you know anything about the factories?
In North America, they had a lot of them made in Japan. It was quite a big market for them over there, when them being used in calculators. So a lot of early calculators had a Nixie tube display of some sort. There were several different makers in Japan that made them, and they actually made tubes for burrows. In addition, there were also tubes made in the UK and all across Europe. Siemens, guys like that were big. Anybody who was big in the tube world also made Nixies to some degree.
Was this similar to the adoption by the USSR where the rights to the tech were simply ignored? Was it licensed outside the Soviet Union by Burroughs after the acquisition of the tech from Haydu Brothers?
I don't honestly know the relationship between Burroughs' technology and the makers in Japan and Europe. The tubes don't look that similar, so I'm not sure that there's any type of cross licensing involved. The numbers are different, the pinouts are different. Likely somebody simply looked over somebody else's shoulder, saw what they had, and then went and figured out how to do it on their own. As far as I know, Burroughs never licensed anybody.
So essentially, this is something they had in America, and then getting protection for that in the Soviet Union and elsewhere was hopeless.
Well, patent protection is very limited. It's only good for 17 years, so it comes and goes pretty quickly, but there were lots of other makers. Nixie is a trade name, but that type of tube was made by many people. There were also some clever things that were done by other people that they didn't do here. The eye sees by contrast, not by brightness. So when you look at something, if you have, for example, black text on a white page, that is very readable. But if I put black text on a gray page, it's very hard to read regardless of the ambient light. The same is true with Nixies. If the background is black, then it's very visible. If the background is lit by ambient light, it washes over the display. That's why it's not good in sunlight. But people learned that if you put a contrast filter over the tube, like a red or orange contrast filter, you could dramatically improve the readability of the tube. In Europe, a lot of these tubes were dipped in a red transparent lacquer.
So that's the reason for the red tubes from Europe.
Yes. It improves the contrast, which makes the tubes way more readable. So many tubes were offered both ways, with the clear tube and the red tube, but that was never done in North America. That was strictly a European thing.
Wouldn't the orange hue of the digits blend in with the red coating?
No, the bulk of sunlight is yellow, so it's largely screened out by the red filter, and there is little reflection on the back. The orange color transmits through the red filter very well, meaning what you get is a bright orange-red character against a black background which your eye goes, yeah, I love that I can completely understand what I'm looking at. If you take a Nixie tube and you just put it out in the air, it's simply not that readable. So some optical engineering is required. People used circular polarizer filters, gray, yellow, and red being very common. The same is true with any other display. You always want to make the background as dark as possible and the segment as bright as possible.
Do you have any advice on driving these tubes?
It just so happens when they were popular, IC manufacturers like TI and so on immediately saw the value in that display. One of the first sophisticated parts that they created was the 7441, which mated with all the 7400 series TTL logic and could directly drive a Nixie tube, which is amazing when you think about it, because there is a 5-volt logic able to interface directly with a 170-volt tube. It was really quite an achievement. One little IC solved the problem, and now counters could directly drive Nixie tubes. Later, they went on to produce other drivers like 7447s that would drive 7-segment LED displays and run Numatrons. But the technology to use a Nixie really required a decade counter that had individual 0 to 9 outputs. That was easily done in an IC 7441. You can still purchase the Russian equivalent today on eBay.
Oh, is the driving directly from the chip?
All you have to do is put it to ground. The problem is that before you pull it to ground, it's potentially sitting at some high voltage. Guys use MPSA 42 or some other high voltage NPN transistor, which has got maybe a 200 or 300 volt breakdown, and when they are interfacing it to a microprocessor, they use a transistor to drive the cathodes. They usually multiplex it when done in that fashion, although some will use individual outputs.
Is the switching time a problem with multiplexing?
Your eye has a certain latency. That's how TV works. With a CRT, you're getting 24 frames per second or 60 hertz interlaced on a CRT. The whole concept and what makes that work is that your eye is slow. It integrates that all together, and you see an image, a movie image or whatever it is doing. But if you try to shoot it with a camera, you'll see that moment during the interlace where you see part of the image. That makes it very difficult to photograph either a CRT directly or a multiplexed digital instrument, because the moment that you take that photo, it's scanning through digits and it is not integrating it the way your eye is doing it.
But can a Nixie tube do that? Can you multiplex a Nixie tube?
Oh, of course. Absolutely. People do it all the time. Calculators were made that way.
But doesn't it take a while to turn on the tube given the striking voltage? And after the strike, don't you meter the supply down?
You don't have to worry about it. You hit it relatively hard so that it's on quite bright and it stays lit for a brief period. It doesn't instantly go away. If you scan the digits on your 16-digit calculator quickly enough, your eye recognizes them as all lit, but they are a little bit dimmer. That's how the eye resolves it, being on only 1/16 of the time.
But the actual supply, the way I'm imagining it, is like a little mountain and then it goes down in terms of voltage. How does the supply electrically work?
The supply is like plus 170 volts. It might be regulated, but we are only talking about 2 or 3 milliamps of current.
Does it just draw its own current?
It draws it briefly while the digit is lit, and then it doesn't draw anything. Then you come along and draw current through the next digit, so whatever drop the supply might have had is actually continuous, because there is always one digit on. Therefore, it's not really a thing.
But if you turn it on, don't you have to strike at 170 volts and then maintain, say, 60 volts?
All you have to worry about is that the anode is tied through some resistance to limit the current to whatever that safe value is, say 3 milliamps, and supplied at least plus 170 volts for a North American tube. That's the extent of your design worries. The rest will take care of itself. All you have to do is take that cathode and ground it. As soon as you ground it, current will flow through it and the cathode will light up and you're done.
Okay. In some of the documentation, it says do not solder. What do you think? When you design, should you buy a socket?
Well, some tubes are designed to be soldered in. They have long flying leads, so some of them were made that way, but the majority of North American tubes were all plug-in. Particularly in Europe and Asia, they were soldered in. Certainly in calculators, they were all soldered in. And there were Japanese tubes sold by Burroughs that were soldered in. That was quite common, although you could also plug them into a socket.
So, given Nixie tubes are prized for their aesthetics, what do you think the role is between functionality and the aesthetic appeal to the user in general? How do you balance those two as an engineer or designer of electronics?
Well, whenever you're designing something, you always have to factor in what the user wants. Part of the reason why people use Nixies to make clocks now is that they look so great. 7-segment displays just look boring. Nixies look like little campfires. They're just interesting. They look good. They look tricky and interesting. And they are kind of three-dimensional because the characters go back and forth within the tube. They have a certain aesthetic quality that's different to duplicate in any kind of 7-segment display. Part of the reason why they are experiencing a renaissance is that they go to that aspect of design which is something that just looks interesting. It makes the whole experience more thrilling. I mean, a clock that is not that thrilling of an object, why in God's name would anyone want to build them as a hobby or devote a year designing a product so people can build a clock? But the reason is simple. They just look cool.
People literally cannot stop designing clocks from Nixies. If you go on Kickstarter, you will see like 5 Nixie clock projects and likely more to come.
They have achieved now what they were unable to achieve in their heyday, which is extreme appeal to the technophile. At the time they were cool, but they were very expensive. Back in the day when $10 actually meant something, if you had a tube, that was $35 a piece, and it took 6 or 7 to make a counter. That was a lot of money. They were a great solution, but not a cheap solution. That is what really drove the creation of 7-segment displays, which were predominantly a cheap solution.
Even with the development costs of silicon.
Oh, sure, yeah. LED displays are cheap.
Huh, but were they always, even in the beginning?
Well, in the beginning, an expensive one might have been $5 a digit, which is still a far cry from $35. Look at how complex a Nixie tube is. Look at all the mechanical steps. There's no way that was ever going to be cheap technology. It never became cheap. There was never a moment where Nixies were, $3 for $1. It just didn't take place. The issue here is that they solved the problem in a wonderful way, but they did it with a high cost. Even today, when Delabor makes tubes, they're not cheap.
Around $300, I think.
Yeah, they are high cost, but people are prepared to accept that because that is the look they want.
From what I have seen, a large amount of those are for corporations that want a cool custom tube or a clock in the foyer.
Or just because they want one as it looks cool.
Yes, that too. There are probably quite a few people like that. Anyways, thank you so much for the interview.
You're welcome.